All right, welcome to the start of a new week. Anyone have any questions or concerns going into today? Good, good. So where we're at, uh, just kind of get us an update. Oh, I forgot to do that. So we're going to take a direct look at derivatives today. So what we left off with on Wednesday, the 2 points becoming 1 point, and that tangent line being our instantaneous rate of change, that's what we're going to look at today. We'll look at a technique for doing that, and we'll go there. Wednesday, we're going to get into some shortcut rules where we'll actually be taking the derivative, and we'll get a derivative that's actually a function, and that'll be really cool because it's, like I said, it's as long as you can subtract one and multiply by, you'll be fine. Okay, you'll see that primarily what we're doing is pretty good. Next Monday we have a holiday, so we don't have class. If you wanted to, you're welcome. You could see that on the Tuesday, Thursday. They have class on that Tuesday. What I'm suggesting is if you wanted to, the test goes through 11.3, so if you wanted to, you could get a week ahead, and then you'd have this whole week for review if you wanted to. Otherwise, we'll do 11.2 and then 11.3. We'll have a day for review, and then we'll have our first exam. I believe that's September 18th, Monday, September 18th. Okay, you'll notice on the Monday before that the Tuesday, Thursday class has to pick up 11.4, which is actually something we'll pick up after the exam because it won't be on the exam. So, but that's just kind of an overview of where we're going. What we're going to do is dive into this discussion of what the derivative is. So far we've been talking about what kind of change? Average rate of change, right? Average rate of change, and it's been a secant line. So we might have had a graph, but we chose 2 points on that graph. We could make a secant line, and then we could get the slope of that line. And we can get the slope of any line if we take 2 points. Let me let's turn this thing off. So that's what we're going to dive into today. A little bit more formalized proof of what we were talking about on Wednesday, that if we combine this concept of a secant line with the concept of limit, and we take the limit as the 2 points become 1 point, that's what we're going to do. So a little bit more formalized look at that, but you're going to see the technique we're pretty much using is we're still just finding the slope, but now we're going to find the slope of a tangent line. Okay. So here's an example. The price of gold, we took a look at this graphically, and this was one where we were finding average rates of change, right? We were doing the secant line on Friday, and I also said, well, what if these went together? So we're going to do it the same, but instead of talking about A and B, what we do now is we choose 1 point, so we call that A, sort of the starting point. But instead of talking about some other point B, what we say is, well, let's just add a little bit more to that point, right? That gives us a second point. And then what we do, instead of changing the coordinates of that point, what we do is we change H, which is a distance. H is a distance that we've added to A. So we take some point, add a distance to it, gets us to another point. And as we bring them together, we'll have this slope formula. But does this really look like a slope formula? I can see 2 y values being subtracted in the top, but I don't see 2 x values, do I? Or do you? But they're there. They're just invisible, right? Because actually what was here, so if this is 8 plus h, it was 8 plus h minus 8. So we had a minus 8. So that went with this value here, and this was really 8 plus h. And notice how the 8 and the minus 8 cancel and leave you 0. So that's one of the things is when we use this difference quotient or difference equation, we don't see it as a slope, but that's all it is. And then we're letting the x's go together. We're going to basically just look at when this goes to 0. But so these cancel out. We have the h. But again, when we talked about when if the denominator goes to 0, what happens? We get division by 0, and that's called undefined, and that's where we were having our problems. So that's where we bring in the limit. Okay, so we're going to see that this will all work. They do it numerically, so they use this slope formula, and they plug in 1. So this would be the point 8 and 9, right? 8 plus 1. And so if we did that, we'd see that if we looked at that graph, I think we may have looked at those two specific ones. It's a horizontal line, so it has a slope of 0. But as we let h become smaller, so 0.1, so this is now the 0.8 and 8.1, they're closer together, we start seeing that the slope gets closer and closer to -5. So on this, actually I added it this time, I adapted the decimals and I put it so, okay, so I've got my my initial point starting at 8. H, let's kind of do what they want. Let's start it at 1. And so we see that that was the value they had. So h is 1. So this is actually 9. And when we do it, we see that it has a slope of 0. So we can see the graphics and everything. We see the calculation. Then as we move, well, we're not really moving the point. What we're doing is we're letting h become smaller and smaller, right? The distance between the points to go down. So I guess I should do this. So I'm making h smaller. And we see down here the slope is going to negative because it's going down. It's getting away from 0. And it's getting, there's 4.15, -3. As they get closer, -4.95. But if they were actually equal together, if I get h equal to 0, it's undefined, right? So what we're going to do is, this is the, as we got closer and closer, we're going to say that the limit should be -5. And again, we're going to get ways to actually do this. If we could draw this tangent line accurately, which this system won't let us do it, but we could actually take 2 points on this tangent line and we could find its slope, and if it was the right tangent line, we'd find that that slope was actually 5. And that's in the homework, that's what you're going to be doing a lot. There's, I don't know, 5 or 6 of these where they give you a graph, they show you the tangent line, and you just have to pick 2 points off the tangent line, and you'll find the slope, and that's what the derivative is. Okay, so we moved from getting the slope of a secant line to now getting the slope of a tangent line. And what do we have? No longer is this an average rate of change. This is a instantaneous rate of change. It's what's happening right this second. And again, that's very powerful for making business decisions. And it's especially if you can kind of see into the future, oh, this is how our business goes. These are the business cycles, and so we can expect this. Okay, we're taking some losses right now, but if we could just hang on, whatever this time is, it might be a couple weeks, it might be a couple days, our profits are going to go the other way. And so that's why people do, you know, I always wonder, some of these big companies, you know, they're losing $50 million. I go, how could you afford to lose $50 million? Well, they're big, first of all, but they also know that we do this every year. We lose $50 million about now, but we're going to switch it. Yes? So the tangent line is like when the points are very close together? So close together, they are. And the derivative is when they are together. Yes. And so we are going to, there's a synonymous, the derivative and the slope of the tangent line are the same thing. So we'll say, give me the slope of the tangent line. I said, I'll give you the derivative. Well, they're the same thing. They really are. So I could call this, the slope of the tangent line is going to be -5. The derivative at this point is -5. Now notice this function has a lot of different derivatives. It depends on where we're at. We will get different derivatives. We also get function values here. So that's one of the things as we go through here is to be careful not to confuse. is that sometimes they'll ask what is the function value, right? Here's an input and here's an output. Other times they want the instantaneous rate of change. So it's not the function value, but it's how it's changing. And notice the function value itself is positive. It's somewhere between 1400 and 1405. Maybe it's I guess 1402. So that's a function value, it's a positive value, but the slope is changing, so it means it's going to go down and then it'll go back up. Okay? But you see how that works. It's this application of limits. So far, what you're going to need to do on the homework is not so much apply limits or something, but just know that what you were doing previously with limits, that it worked, and that numerically we saw it sneaks up, that this slope is going towards -5. Graphically we did it, and then that's what's going to happen. And so if I have a tangent line, all I got to do is find that slope of the tangent line, and I'm home free. I've got the derivative. Okay. And that's exactly what they say, is that looking at this table of values, numerically they've done it. We threw in the graphical. We can say the instantaneous rate of change at 8 o'clock in the morning was -5. So and again, this was the price of gold. So the price of gold was dropping by about $5, $5 per hour at that time. So that was already, of course, yeah. Yeah, thank you. You pick up your units from the table. So again, this is just some verbiage that says basically what we've been doing, that this difference quotient takes a starting value A, adds some distance to it, 1, and then it makes that what it's adding, it makes it smaller and smaller until it goes to 0. And notice we've always got this limit as h goes to 0. So the distance goes to 0, so they become, we're talking about 1 point. Of course, mathematically, that gives us something that's undefined. But with limits, what we've been talking about is that we've actually got it. And so we call this taking the derivative. We call it differentiating the function. Yeah. The cool part is we're not going to have you use this formula a lot. Now, if you were in the engineering calculus, we'd spend a whole week with that formula, because it's if you've got square for linear equations, it's not too bad to work with, but if you've got squares, it gets really messy. And if you had cubic functions, it's really terrible to work with. The mathematics, like I said, the mathematics behind it. What we're doing is we're just saying that this does exist. We used to give you a whole day of doing that difference equation. We're not actually going to have you use it at all. We're just going to have you accept that that's the magic behind of what's going on. And we'll take a look at the homework. We'll see that we don't really have you doing that. So again, it's just say we're going to start at some point. We'll call it A. We use this, and as we let A go to 0, as long as it exists, that's what we call the derivative. And the derivative we write as f prime. So that little thing, and we're getting the derivative at a particular point. On Wednesday, we'll actually look at how to take to use some shortcut rules to actually take the derivative for the whole function and have a function that's a derivative. Okay. And again, a couple rules. It must be an interior point. It won't work at endpoints because we don't. One endpoint we don't know what happened before. The other endpoint we don't know what's happening afterwards. So we can't really take a derivative there. And again, what we're going to give you fits these things. The above limit must exist. So yes, the exhibit has to exist. Which if it doesn't exist, then yeah, we can't take the limit. Everything we're going to give you, the limit exists. And then when it does exist, we say it's differentiable. Okay, so again, a lot of stuff that's there, but what are we going to be doing is we'll be given a graph. So far, we were looking at the secant line, so that pink color, and we were taking it, and this gave us the average rate of change. And notice this, the slope. The average rate of change between those 2 points. If we take the tangent line and we get the slope of that tangent line, we get instantaneous, and I'll just abbreviate that as INST, period, instantaneous rate of change at the point A. And again, A is just our starting point. So A plus H, and we make them together, and that's all we're doing in this. And that's what we're calling the derivative. That's the whole first part of the class. And then we're going to get some techniques to actually just from the function to be able to get a function that gives us that. We plug in a value, we've got the slope of the tangent line, we've got the derivative, all the same thing. Okay, but again, we're getting instantaneous rate of change. And over here, we get another instantaneous rate of change. And we'll see some things that change very quickly. So we could go from a negative rate of change to a positive rate of change very quickly. And so sometimes, and some of you have talked to me, you're in finance, the timing on when you buy and sell can be very critical. Could be within minutes, right? Sold this minute, you made a bucket load of money. So this minute, you lost a bucket full of money. It's, it can be that critical. Okay, so the idea is how do we draw a tangent line? The good news is it's so difficult to do that we're not going to actually have you draw the tangent line. We'll give you problems with the tangent line already drawn. And I'm going to show you, because I figured out from students that how to figure out what that slope of that tangent line is. You don't just look at it, it'll actually help you. So the idea of a tangent line is it touches the graph in one place. However, that's not always true. There are some places that where the graph might look like this, where this is the tangent line at the point P. It's touching at that one point, but because of the way the graph goes, the back part goes back into the graph again. So you could, if you went from P to Q, that is a secant line between those 2 points, but that's not what we're interested in. At P, it is a tangent line because it's touching just there. And there's another example here. We'll see that what's happening here, this is when P is I forgot what it's called now, inflection point. So you'll see that the rate of change is actually changing right at that inflection point. So at the inflection point, the tangent line actually goes through the graph. So that can happen, yes.
So off a secant line, you can always create a tangent line on the other point?
You can, yeah. By moving them together. Now, they won't always look like this, but yeah, if the function's like that, we could have that secant line also happens to, because of the way it is also a tangent line. Yeah, the key part, as we're going to see, is we just focus on P. As long as it's just going through there and sort of following through, that it really only goes through one of the points. It's not going through 2 or 3 of them. Okay, then we can say that's the tangent line. And the good thing is it's really difficult to draw a tangent line. We're going to give them to you, but we just want you to see that. So like this one, as we get closer and closer, now that would be what we kind of think of a tangent line, is going through the graph at one place. But this sort of violates it, but it just says, well, let's forget about that part. Let's look closely. And we see what's happening as we get closer and closer. It does look like the tangent line actually, the graph actually follows that tangent line pretty good. And so that's what's happening. As you get close enough, everything that's called local linearization, everything is aligned. If you get, you might have to use a microscope, but you get really close, you can think of everything as a straight line. It might only be good for 1 or 2 seconds, but it's a line. So this one is getting us close. That's why we can use the slope of the tangent line for just that instant. Of course, the next instant, who knows, right? Is that okay? Okay. So again, we get to here. So far, everything is building up. We're just now getting into what we're going to do. Really, Wednesday we'll get into the nuts and bolts of calculus, of doing it. All of this stuff is just to get you to believe that that limits exist and that we can do all this stuff, because otherwise we really can't. So this is an example of what we're going to have you do. This is actually from the homework. I'm going to go into the homework because it gives you some good information. So how do we find the slope of this tangent line? Well, we have to pick off 2 points on this tangent line. So I think this is a pretty clear point. It looks like the point 1, 1, 2, actually. That's 1 point. And then maybe take this point up here. And again, sometimes it's hard to tell whether it's really going through that point or if it's close, but I'm going to show you in the homework, if you click on it, the alternate text will actually tell you what 2 points are. So you'll pull those off. But what we do is, okay, if that's a point, that's 3, 8, right? So I just need the slope of this tangent line, and that's what the derivative is going to be at whatever point this is, what it looks like x equals 2. Right? So it looks like we've got this point here, 2, 5. I'm going to show you a technique I use from ancient India. It comes from like 3,000 years ago, and I found it worked for taking the slope for me because I'm dyslexic, and whenever I put in the slope formula, I typically will have problems. So this is a technique called vertically and crosswise. If you've got the points lined up here, right, the first one is the x, the second one's the y. If you just line them up like this, let's subtract the x's, so 1 minus 3, negative 2. Subtract the y's, 2 minus 8, negative 6. Then you take the x, and again, this is the difference of the x's. You tuck it underneath the y, and you now have your slope. But if you're like me, you didn't have to put the y's over here and subtract them and the x's and get them in the wrong order and mess everything up. And you just went straight down, vertically underneath. This slope is going to be negative 6 divided by negative 2, which I think is positive 3, right? Now you can put that in the slope formula, do the same thing. So we could have gone 8 minus 2 over 3 minus 1, and we would have got 6 over 2, which is 3. Same answer, whichever way works for you. I just find when I started doing this, I found this about 10 years ago. That's how I do slope all the time, and I don't mess it up. I go up there. I typically, especially if I got a lot of other things going on, I get things in the wrong order or something. Sometimes I put the x on top, the y on bottom. Yes. They were the ones I saw. So I could have taken this one, but then I'd have to estimate what that is, right? So I could see that this was going through the crosshairs. That's the only way I did it. And I could have chose this one too. And I probably would have got a pretty good, I should have got the same value. Let's see, I would get 1 over 3. Yeah, I'd get the same value. So these are all good points. All 3 of those are actual points that would have given us the same. Doesn't matter. As long as you take 2 points off of it, because we've got a line, the slope is the same. That's what the nice thing about lines. The slope is the same everywhere on that line. Okay. Cool part is, again, when you do the homework, don't try to pick it off the graph because that's, as good as you can try to get it, it might not be right. But you're going to click on the graph and it's going to tell you the 2 points. In fact, let me show you right now, since we've got talking about it. Let me get into, let's keep those for now. While this is loading up, the other thing I will do is this Friday, I will update scores. So the first set of homework is due 9/1, which is this Friday. Typically what I do is, there'll be some of you who are still scrambling to get some of the homework done. I will move it to about the test. Because basically, as long as you get it done by the test, you're fine.
How do you determine what coordinate pair comes first in the slope equation?
Doesn't matter.
Oh, so
Either way, yeah.
it's like, okay.
Yeah. And notice how I did it two different ways. One of them gave me a positive over a positive, the other one gave me a negative over a negative. So the order, but they both end up being positive slopes.
So if you switch your, like it's y2 minus y1.
Yep. If you do y1 minus y2, what you'll do is the signs will be different, but the end result will be the same. So if it's negative, you might have the top negative, the bottom positive. The other way will give you the top positive, bottom negative, but you end up with that's one of those things that it doesn't, that's okay. The problem is if you use y2 and x1, that's what I typically will do, and that's where I mess up. See, we're in 10.5, so let's just, I'll do a preview. And so, yeah, so like this one, they give you the graph of the function, they give you the tangent line, they want you to estimate it, and again, okay, you're going to pull these, but just click on it, and notice it gives you all the information. And you don't have to read all of this. What I find is it talks about the line here. It's talking about the curve up here. We don't want the curve, we want the line, the tangent line, and it gives us a point, 2.2 and 4.2. Who would ever be able to pick that out? I couldn't do it, right? And 3.6, I could probably pick that. You could probably see that. But anyway, use the points they give you and you'll always be right on track. Because there's some in there that you go, there's no way I could come up with 0.26 or whatever they come up with, but now you can. And that's how I had a student tell me, I was stuck. I don't know how to get the right answer. He says, oh, just click on the thing and it gives you the points. Oh, okay. So as you find tricks and stuff, please fill me in, and then I'll help the next generation as we go through these things. So, but you'll see there's that question. Here's another one. Yeah, that does look like a zero slope, but if you click on here, you could see, yeah, it's going to be a zero slope. It tells you it's a horizontal line. So you actually don't have to do too much. Okay, slope is zero, right? But a lot of these, again, click on it. It will give you two of the points. You'll do it. Some of them you could probably pick them off the graph and you'd be okay, but this is the safe way. It's going to give you 2 points. Use those 2 points and you'll match their answers identically. So the slope of the tangent line. The derivative of f at that value. So what is the slope of the tangent line? It's also the derivative. Same thing. Yes, sir.
So if the vertex of any function, the derivative is going to be 0.
You got it. And we're going to see that because a vertex is either a minimum or a maximum. That's how later on we're going to, how do I find the minimum and maximum? Find where the derivative is 0. So we're going to get those techniques. Exactly. Good. So you start to see these patterns, and it's calculus where all these things match up and you're going, wow, this is kind of cool. It's like almost somebody planned our world out. It's mathematics in our world, in the physical world, really work together. Okay. And you get these things that, it's the idea of a limit. It doesn't really seem like it should work. Now, some of these is going to ask you, now they didn't draw them, but you're going to have to sort of visually put in a tangent line here. Okay? What I want you to know, because when I think of a tangent line and a slope of a tangent line, I'm thinking that the slope is greatest when it's steepest, but it's not necessarily. If it's negative slope is always less than positive slope. Even if it's like a narrow slope and it's going down real fast, negative is always less than positive, is the way they're thinking of these things. So again, they won't draw them in, but they will make them sort of, let's see, I can actually put them in here. You sort of have to estimate. There's that one. Yeah, this one's kind of going to be a zero slope. And this one's like that. And so, okay, I've got a negative, a zero slope, and a positive slope. Which one's going to be the biggest? Well, the positive slope. Okay, I can't tell you exactly what it is. You don't have to calculate it, but that's going to be the greatest. The one that's going to be the less, the negative slope. Okay, zero, because negative is smaller than zero, right? So, but be careful. Sometimes I think about this question as far as steepness, because that's a sort of greater change. But what they're talking about is sort of the value of the slope. So positives are the biggest, zeros there in the middle, negative slopes are actually less than 0. Yeah. So you can. So there'll be some that you judge that way. Cool. Let's get out of there. And again, there's several of those type of things, and you just sort of visually going to have to see which one is which. I think you can, and I mean, you could click on these, but these ones are more a visual, and you know, there's some questions to answer and stuff. So I think you'll be fine on those. We'll see again, and we'll have time to answer maybe any questions as we go through. There's really not too much more. What? That's the last of the slides. In fact, there's nothing more. So that gets you ready to go through the homework. That's all there is to it, is the derivative is the slope of this tangent line. So we're going to give you a tangent line, find its slope with 2 points. So we're still doing it that way. But it gets you this idea that that tangent line is the limit as a secant line. The 2 points of a secant line became 1 point. That's what they're drawing for us. And again, they're difficult to really draw accurately. Again, you need a very accurate graph. You'd have to, you know, get a straight edge and everything. We're not going to go there. We're using technology. And again, we could pick the lines, the points off of here for a number of them, but there's some that they're just not going to, you know, it looks like it's going through 2,5, but it's not really, but we wouldn't know that until we click on this thing and it tells us that it's going through something different. So we do that. The concept today is that the slope of a tangent line is also the derivative. They're two different things, but they're the same two different things. We use them for the same thing. And then what we're going to do is we'll take this jump and we'll see there's a connection between a function and its derivative. And basically it's just one step down. So we're going to, and I'll throw away the big suspense. So something that's an x squared, if I have a function that's an x squared, a quadratic, the function for its derivative will be a linear equation. If I have a cubic equation, x to the third, blah, 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 its derivative is going to be a quadratic equation. If I have something x to the fifth, its derivative will be something x to the fourth. So it's kind of cool. And again, I remember learning this the first time, I said, this can't be, it's too easy. Really? It's always going to work? I didn't believe it for a long time until I started teaching it, and it does work because it's patterns. It's patterns. And we could do it again and again. But that's what I mean is all we're going to have to do is subtract 1 from that exponent. We'll get the derivative. There's also a few little things that happen, but
Is there no derivative on a linear line then?
a linear equation becomes a constant. So the slope of a line, right, that is the rate of its instantaneous rate of change is always the same. Good. I had never thought of that. I just picked that up right now. So see, you ask a question and I learned something too. It's like, yeah, it's always a constant. So actually when you take the derivative of a line, what you get is you get a horizontal line. Y equals 3 or something. So yeah, so the slope of this line, so if this was our function, if we erase this, the slope of the tangent of this line is 3 everywhere there is. And so the derivative function is just y equals 3. Cool. So almost not even worth coming in today, huh? So we're done early, but what that does is it gives us time. If you have some questions on the other homework, I'd be happy to work with you. If you want to stay and start working on the homework, I'd be happy to work with you. If you want to get out of this heat and get, before the traffic gets too bad, that's fine too. So.
Help with this problem on the
Yeah, let me get out of the recording. So.